Hello, everybody. This is the week one subjects in the course of MATH2099. This is the tutorial part. That's what we've done in week one. So this is like a review for you for your exams or whatever you want to learn. For the course MATH2099 and at the University of New South Wales. Here in the first example, we are studying matrix multiplication, basically, to understand how matrix multiplication is defined. You cannot multiply any size of matrix, any size of matrix. You need to have some requirements for it. So in that question, the question is there these matrices are given and we have those matrices do some addition, some multiplication, and the questions is that which ones are can be defined and can be calculated. So multiplying a number by a matrix is a multiplications with every entry. So if you're multiplying with any, for example, is 2 minus 2b, which means that you're multiplying minus 2 with every element in this matrix, and it is possible to do that. So this is an A matrix and this is a B matrix, and this is an addition. You cannot add them because the sizes are completely different. It doesn't make sense. And B minus C, B and the C are exactly the same size. There are three rows and 2 columns. C has 3 rows, 2 columns, so we can add them. And multiplying with any scalar makes perfectly sense. So we can multiply every element here by minus 3 and with that one. So it is possible to do that. And the next question, is BD. Would it be possible to multiply B and D? That's the focus area for me in that moment. So B is a matrix of 3 columns, 3 rows, 2 columns, and D has 2 rows, 3 columns. Matrix multiplication is first matrix, the rows of the first matrix, we multiply with the columns of the second matrix, and we write it down in a corresponding position. So if you want to, this multiplication is possible because when we multiply this vector with this vector as like a dot product, then it has to match the number. It means that you must have 2 columns, whatever the column number here should be the row number here. So this 2 is this 2. So these 2 are exactly the same. So it is possible to be able to multiply them. And this 3 and this 3 is relevant. In that sense, the nth matrix, the multiplied matrix, will be the size of this, the size of this in a row, and size of this in the column. So if you want to multiply a m by n matrix with the BRS matrix, you require this number is equal to that number, which means number of the column in the first matrix should be equal to the number of the rows in the second matrix, such that the matrix multiplication will make sense. Matrix multiplication, again, is the row vector multiply with the column vector as a dot product, which means this vector multiply this vector. So we will have minus 2 times 2 is minus 4, and plus 1 times 1. So it is the dead position. This is the first row, first column. This is the 1, 1 position in the multiplication. And this row with this column, minus 3 times 2 is minus 6. That's minus 6. 1 times minus 2, that's minus 2. So this row with this column is this element, because this is the first row, second column. This is the first row, second column. And this row with this column, we will have minus 2 and plus 3. Minus 2 plus 3 will come to this spot. I think you got the pattern. So this is how we multiply it. Yes, it is possible to multiply BD because the sizes are okay. And when we complete these calculations, as we've done here, we will obtain a 3 by 3 matrix. And that will be the result of it. Okay, I'm not going to go further. I think you that explains the everything needs to be done. And if you want to do other parts, you're welcome to do it by yourself. It is very important. Next question is about solving the linear system of equations. It is very important for all students should be able to solve linear system of equations regardless. So we have a matrix. This is called coefficient matrix. This is a 3 by 3. And B is a column matrix, and X is the unknowns. So the system AX is equal to B. This is what we would like to solve. With the matrix multiplication, this row with this one, where you have an equation basically, x1 minus 4x2 minus x3 is equal to 12. This is one equation. Another equation will be minus x1, 3x2, 2x3 is equal to minus 7. That's the second equation. And the last equation comes from the multiplication with this row column is equal to 35. That's 2x1 minus 9x2, 2x3 is equal to 35. That equations through that is exactly the equivalent to work on this matrix form. We would like to write it down equations, number of the equations in this fashion, because then we will be able to write down some algorithms, ask for the computer to do it, and then we can improve some theories on the top of it. It is nice to be able to do that rather than working out within equations. And we know that how we solve it. How we solve it is first, we write it down the augmented matrix. What does an augmented matrix means? We write the coefficient matrix A, and then we, in the last column, we put the column vector B. In order to be able to separate that from the coefficient matrix, we use a line emphasizes that. So this is the coefficient matrix, and this is the right-hand side of the equation that we have. Then we apply the row operations. In the row operations, we can add any row by multiplying another row with any scalar to it, and then add the row. We can swap the rows, or we can multiply the rows with any multiple of a scalar. So there are 3 row operations that we can do. By using the row operations, we would like to find the reduced row echelon form of this augmented matrix, and that will give us the result. There are 3 options that we can obtain. One, we can obtain a unique solution, or we can obtain no solution, or we can obtain infinitely many solutions. For each of those systems, we have some possibilities. Let's work it out. What is the solutions for this system? Okay, what is the reduced row echelon form and how we can produce? The idea is that to find out a kind of an identity, this is an identity matrix. We would like to find out this kind of matrix or in a corner, if you have a larger matrices or anything, you want to find out this kind of structure as much as you can. That's the idea. So the first one, we want 1. This position needs to be 1. That's a start with. We are lucky in this question. This is 1. We don't need to do anything for it. And we want this position to be 0 and this position to be 0. Our focus is that make those positions 0 by using the row operations. To do that, if I add this row with this, if I add this row to this row, I will obtain 0 in this position. So that's what I'm saying here. R2 is equal to R2 plus R1. For this position to be 0, I need to multiply this row with the minus 2 and add here. Only my focus is this position and this position. Okay, the second operation, I have R3 is equal to R3 minus R2. These two rows are independent from each other, so I can do it at the same time. The first row will not change. That is 1 minus 4 minus 1, 12. And the second row is just an addition. This time, since this was 0, this one will be minus 1. Add these two, I have 1. If we add these two, we have 5. Now, this row, we are going to multiply by minus 2 and add with this one. This position will get 0 for us. This one, minus 2 times minus 4 is plus 8. 8 minus 9 is just minus 1. Minus 2 times minus 1 is plus 2. And you have 2 here. 2 plus 2 will be 4. This multiply with minus 2, we have minus 24. Minus 24 plus 35 will be 11. Okay, now we want this position 1 and this position 0. For that, we can multiply this row with minus 1, add with that one, and then we can multiply this row with minus 3 so that this position will turn out to be minus 1. There are different, so the row operations are not unique, of course. You can do other row operations, but the key idea is really to obtain this kind of structure, identity type of structure, as much as you can, as much possible as. So, okay, what we can do here, we are multiplying this one by minus 1, adding here. So this position is 0. Minus 1 plus 4 is 3. And then adding this one minus 5, that will give us plus 6. And we multiply this row later on with minus 1. So that will be 1 minus 1 minus 5. We obtain this one. Now we want to obtain this position is 1. We can multiply this row with 1 over 3. Then we have this position 1 and this position will be 2. Now I can go backwards. Some people stop here and go back to the equations and solve it there. But it is okay if you want to do that. But I think it is better to keep going to the row operations and find as much as the identity matrix as possible. This is the reduced form. This is the echelon form, and this is the reduced row echelon form. This is as far as you can go. And this is just another an echelon form because you have the leading coefficient 1 here and you have zeros underneath. Okay, now I want this position 0. This position 0, this position 0. I can just add row 3 to row 2 and row 1, and these two will be 0. Okay, this is what I need to do. That's 0, that's 0. If I do that, this one addition with that one, I will have minus 3 in this position. If I add this one to here, I will have 14 for this position. Now, only thing I left in here is this position. So I have 1 here and all the other 0. If I multiply this one with plus 4 and add to the first row, I will obtain this position 0 and all the zeros remain 0. I will not destroy the structure that I would like to get. So this is that. This will be 0. When I have 4, I'm multiplying this by plus 4 and adding it. So 4 times 3 is 12, but this is minus, so minus 12. Minus 12 plus 14 gives me 2. So this is the reduced row echelon form of the augmented matrix. We know that this is the coefficient matrix. And when you multiply this coefficient matrix with x1, x2, x3, is equal to 2 minus 3, 2. But this structure gives you exactly x1 is equal to 2, x2 is equal to minus 3, x3 is equal to 2. Imagine you're multiplying this matrix with this column, right? 1 times this, just x1, which is 2. This row with this column is just x2, which is minus 2. That's what I'm saying. So this row with this column is just x3, which is equal to 2. So if you find exactly the identity matrix, it means that there exists a unique solution. That is the case in this position. In order to be able to find out the unique solution, your number of the equations match to the number of the unknowns. As we are here, we have 3 unknowns and we have also 3 equations. Then it is possible to find out the unique solutions. There are other possibilities for this one as well. But if you have 4 equations and if you have 4 equations, but 2 unknown, 3 unknowns, you will not be able to find. We will have more equations than you need. Anyway, if you have 4 unknowns, but you have 2 equations, then it means that some of the variables should be dependent, and you might expect that you will find an infinitely many solutions, but you wouldn't expect to find out unique solutions because you don't have enough equation in that case. So the number of the equations, number of the unknowns are important for you. If the number of the equations equal to the number of the unknowns for you, then you may expect to find out the unique solution. It is not absolute. You need to check it. You need to find out. Maybe you will find no solution in the end. So you need to check it. You need to find it. But there exists a possibility to find out the unique solution. Okay, these are the ideas that you need to play with. This question, you have another 3 by 3 matrix. This time, the unknown matrix on the right-hand side, B1, B2, B3, is not known. And we would like to find out the condition on B such that the solution, this equation system has a solution. Okay, so we have the coefficient matrix. On the right-hand side, we have unknowns this time, B1, B2, B3. But we have these unknowns as well. So the equations are known like x1, x2, x3, as we've done before. But we also don't know the right-hand side of the equation. Still, the aim of the finding a solution of this equation is to figure out x's. But those x's will be depending on the b's. Okay, I will not go through the step by step as I've done in the previous question. Again, I want this position 1, this position 0, this position 0. A sensible thing to do, multiply this by -2, add this, -2, add this, 0, 0. And then you get this kind of element. You want this position 0. This is 1. This is a leading coefficient is 1, is perfectly. So get this position 0, first 1 and then 0. And you found this matrix. In this question, we don't have an opportunity to get rid of these ones or this one. We want to understand this condition on B. The last row says us something because this last row, together with unknown vector, x1, x0, xr. What I mean, sorry. So this last row says that 0x1, last row says to 0x1 plus 0x2 plus 0x3 is equal to this B, right? 1 over 3, whatever that is, B3 minus 2B1 minus 2B minus B2 plus 2B1. Right? This one here, this side is 0, and this side cannot be something. It is a contradiction. It is impossible. If you want to have a solution, this has to be 0. This is what I'm trying to say here. This has to be 0. If you tidy up this number here for a while, then you will find 8B1 minus 3B2 minus B3 is equal to 0. The system has a solution for this coefficient system, such that B1, 8B1 minus 3B2 minus B3 has to be 0. So this is the condition that you're looking for. And so you have a solution if you don't have a contradiction. But in this case, if this is 0 and this is not equal to 0, would give you a contradiction. This is not what you want. That's the key for this one. Okay, finding an inverse. Finding an inverse is of 2 by 2 matrices, how we do that, or any other matrices. For 2 by 2 matrices, or is a bit easier. You can do it that way. So if you have a 2 by 2 matrices, the inverse of the two matrices is given by 1 over AD minus BC, A times T minus BC. This is basically the determinant of A. And then you have swap these positions and make this position and this position minus. And then by using this formula, you can find it immediately. If you check it, multiply this row with this column, you will have AD minus BC. When you multiply this one, you will give 1 for this position. A minus AB plus AB will give 0 for this position. So if you multiply this with this one, it will give you the identity matrix. Now, this is a formula in general you can apply for it, but in this case, we would like to practice how we find by using the row operations. That is, you create first augmented matrix, A on the right-hand side, and then the identity matrix on the, A on the left-hand side and identity matrix on the right-hand side. Then you apply the row operations. In the end, of course, with the row operations, you want to achieve an identity matrix on this side. When you ended up in your calculations, naturally, you will find A inverse on this side. This is what I mean. So you have A matrix 4, 5, 3, 7, and you have identity matrix 2 by 2 identity matrix, which is 1, 0, 0, 1. We want this one, we want to make this side, it looks like an identity matrix, which means that we want this position 1, this position 0. We can divide, the first row is 1 over 4. We can divide the second row with the 1 over 3. Then this position is 1, and this is 5 over 2, 3 over 7. Of course, you're applying each row the operations that you are doing. So this will be 1 over 4, and this will be 1 over 3. Then what we have, this is 1. We want this position to be 0. If we multiply this row with -1 and add with this one, you will have 0 in this position. So that's what we are going to do here, 0. So this one is minus times this, minus of this, plus 7 over 3. 7 over 3 minus 5 over 4. You need to make the denominators the same, which is 12. That will be 28. That will be 15. 28 minus 15 over 12. 13 over 12. That's that position. And this position minus time of this, adding here is minus 1 over 4. You have 0 here, no effect here. Now we want this position to be 1, so we will need to multiply this row with the 12 over 13. That is, that will give us, this is 1, and then we have 3 on the top because 4 and 12 will simplify itself. Then we have 13 on the denominator, and negative also moves on here. Similarly, if you multiply this with the 12, you have 4 on the denominator, and we have 13 on the denominator. Now we want this position to be 0. All we need to do, just multiply this row with -1/4 and add here. So that will be 0. We need to multiply -5/4 with this number, add here. This is what I've done here. -3/13 -5/4 plus 1/4 for this position. We'll have 7/13. And if we multiply this with the -5/4, we get -5/13, which is this position. So all of them has the 1/13 is a common factor. I can take it out. So that's 7, that's -5 -3, 4. That has to be the A inverse. We have identity on this part. We have 1 0 0 0 for this here. And on the right-hand side, we have A inverse, as I explained it here. That's A inverse. If you check it out with the formula, you would find out the same result. That times this will be 24 times 7 is 28, -3 times 5 is 15. So this is 1/13. And we swap these two positions. So 7 here, 4 here. We multiply this position minus, this position minus. So it's -5 -3. This is 7 -5 -3 -4, and 1/13 in the beginning. Yeah, Ines, that is that is A inverse, how to find out. And you have a 3x3 matrices. It is, the formula is not as simple as this one. Yes, we have a general definition for the A inverse if it's a 3x3 matrix, but finding a inverse for a 3x3 matrix is not easy. It is easier to use this method here. Take the matrix here, 3x3 matrix here, and identity 3x3 identity and row operations will give you the inverse. That's the better way to handle it. For the matrices over the size. Since it is complicated, we usually ask the computer to calculate for the A inverses us. In these days, we don't calculate A inverse by ourselves, but you need to know how to calculate it. And you need to know what it involves in the calculations. I think for this video, that's it. That's enough. Thank you very much for listening. I hope it is useful for you.